Welcome to Chapter 3 of the Introduction to Nanomaterials series. After learning about synthesis, the next critical step is characterization. How do you know you've made what you intended? How do you measure particle size, confirm crystal structure, or analyze surface chemistry? In this chapter, we'll explore the essential techniques for nanomaterial analysis, from electron microscopy that lets you see individual atoms to spectroscopy that reveals chemical composition. By the end, you'll understand which technique to use for which question and how to interpret the data you obtain. Let's start with an overview of the main characterization techniques. Transmission electron microscopy, or TEM, provides the highest spatial resolution at about 0.1 nanometers, directly imaging size, morphology, and crystal structure, but requires thin samples. Scanning electron microscopy, SEM, images surface morphology at about 1 nanometer resolution on bulk samples. Atomic force microscopy, AFM, gives 3D surface topography and can measure mechanical properties. Dynamic light scattering, DLS, rapidly measures hydrodynamic size in suspension, covering 1 to 1,000 nanometers. X-ray diffraction, XRD, identifies crystal structure and estimates crystallite size using the Schrödinger equation. X-ray photoelectron spectroscopy, XPS, provides surface composition and chemical state information from the top 1 to 10 nanometers. BET analysis measures specific surface area from gas adsorption. Each technique answers different questions, and comprehensive characterization often requires combining multiple methods. Transmission electron microscopy is the workhorse of nanomaterial characterization. A beam of electrons accelerated to high energy, typically 100 to 300 kiloelectron volts, passes through an ultra-thin specimen. Because electrons have much shorter wavelengths than visible light, TEM achieves atomic scale resolution. At 200 keV, the electron wavelength is about 0.0025 nanometers, giving subangstrom resolution potential. In practice, resolution is limited by lens aberrations to about 0.1 nanometers for conventional TEM and below 0.05 nanometers for aberration-corrected instruments. The specimen must be thin enough for electrons to pass through, typically under 100 nanometers. TEM directly reveals particle size, shape, and morphology. High-resolution TEM shows atomic lattice fringes, allowing measurement of d-spacings and identification of crystal structure. It's the most direct way to see what you've made at the nanoscale. TEM has multiple operating modes for different information. Bright field imaging uses the transmitted beam, with crystalline regions appearing dark due to diffraction. This is the most common mode for morphology and size measurement. Dark field imaging uses a diffracted beam, making specific crystallographic orientations bright against a dark background. It's useful for defect analysis and identifying specific phases. High-resolution TEM, or HRTEM, uses phase contrast to image atomic lattice fringes directly. You can measure d-spacings and identify crystal structure from HRTEM images. Scanning TEM, or STEM, focuses the beam to a probe and scans it across the specimen. Combined with a high-angle annular dark-field detector, STEM provides Z-contrast imaging where heavier atoms appear brighter. STEM is also the basis for analytical techniques like energy-dispersive X-ray spectroscopy for elemental mapping. Selected area electron diffraction, SAED, produces diffraction patterns from specific regions, distinguishing single crystals from polycrystalline samples. Getting quantitative data from TEM images requires careful analysis. For particle size distribution, you need to measure a statistically significant number of particles, typically at least 100 to 200. Image processing software applies a threshold to distinguish particles from background, then labels and measures each particle. For non-spherical particles, the equivalent circular diameter is commonly reported, calculated from the particle area as 2 times the square root of area divided by pi. Results are typically presented as histograms fitted with log-normal distributions, which are common for synthesized nanoparticles. Report the mean diameter, standard deviation, and polydispersity index. Be aware of potential biases. Small particles may be missed against background noise, while larger particles are more visible. Aggregated particles should be counted carefully. For crystallography, measure at least 10 lattice fringe spacings and average them. Always include scale bars calibrated from known standards. Scanning electron microscopy complements TEM for surface imaging. Instead of transmitting through the sample, SEM scans a focused electron beam across the surface and collects emitted signals. The interaction between beam and sample produces several useful signals from different depths. Secondary electrons are ejected from the top 5 to 50 nanometers and are sensitive to surface topography. The familiar SEM images showing textured surfaces use secondary electrons. Backscattered electrons come from deeper, 10 to 1000 nanometers, and their intensity depends on atomic number. Heavy elements backscatter more electrons and appear brighter, providing compositional contrast. X-ray fluorescence from 1 to 5 micrometers enables energy-dispersive X-ray spectroscopy, or EDS, for elemental analysis. SEM has lower resolution than TEM, about 1 nanometer, but can image larger areas and thick samples. Sample preparation is simpler, though non-conductive samples may need coating to prevent charging. Atomic force microscopy uses a sharp tip on a cantilever to probe the surface. As the tip approaches the surface, forces between tip and sample, including van der Waals and electrostatic forces, deflect the cantilever. A laser reflected from the cantilever back to a photodetector precisely measures this deflection. The sample is scanned beneath the tip using piezoelectric actuators, building up a 3D map of surface height. There are 3 main operating modes. In contact mode, the tip drags across the surface maintaining constant force. This works well for hard surfaces, but can damage soft samples. In tapping mode, the cantilever oscillates near its resonance frequency, and the tip taps the surface briefly at each cycle. This reduces lateral forces and is gentler on samples. In non-contact mode, the tip oscillates above the surface without touching, measuring force gradients. Beyond topography, AFM can measure mechanical properties like stiffness through force spectroscopy. It works on various substrates and doesn't require vacuum. AFM produces rich 3D data that can be analyzed in several ways. The raw data is a height map, typically displayed as a 2D image with color representing height. This can also be rendered as a 3D surface for visualization. Line profiles extracted along specific directions show height variation with position, useful for measuring feature heights and widths. Statistical analysis of height distributions provides roughness parameters. RAW, the arithmetic average roughness, is the mean absolute deviation from the mean height. RQ, the root mean square roughness, is more sensitive to peaks and valleys. RMax is the total height range from lowest valley to highest peak. For nanoparticles on a flat substrate, you can measure individual particle heights and diameters. Tip convolution affects lateral measurements since the finite tip size makes features appear wider than they are. Deconvolution algorithms can correct for this if the tip shape is known. Height measurements are generally more accurate than lateral measurements in AFM. Dynamic light scattering is a fast, non-destructive method for measuring particle size in suspension. A laser illuminates the sample, and scattered light is detected at a fixed angle, typically 90 or 173 degrees. Particles undergoing Brownian motion cause fluctuations in the scattered light intensity. Smaller particles move faster and cause faster fluctuations. The autocorrelation function of these fluctuations contains information about the diffusion coefficient. For a monodisperse sample, it's a single exponential decay. The decay time is inversely related to the diffusion coefficient d. The Stokes-Einstein equation then converts d to hydrodynamic diameter. d equals kBt divided by 3 pi eta dh, where kb is Boltzmann's constant, T is temperature, eta is viscosity, and d, h is hydrodynamic diameter. Note that DLS measures hydrodynamic diameter, which includes the solvation layer around particles. This is typically larger than the core particle size, measured by TEM. Interpreting DLS data requires understanding its characteristics. The autocorrelation function is fitted using cumulant analysis. The first cumulant gives the z-average diameter, an intensity-weighted mean. The second cumulant gives the polydispersity index, or PDI. A PDI below 0.1 indicates monodisperse samples, 0.1 to 0.4 indicates moderate polydispersity, and above 0.4 indicates broad or multimodal distributions where interpretation becomes difficult. Because intensity scales with the sixth power of diameter for Rayleigh scattering, larger particles contribute disproportionately. Even a small number of large particles or aggregates dominates the signal. This is why the z-average often exceeds TEM measurements. Temperature must be controlled since it affects viscosity and Brownian motion. Concentration matters because high concentrations cause multiple scattering. DLS is best for routine quality control of colloidal samples and comparing batches. For absolute size, TEM is more reliable. DLS excels at detecting aggregation, as even small amounts of aggregates are immediately visible in the correlation function. X-ray diffraction is essential for determining crystal structure and phase purity. When X-rays hit a crystalline material, they diffract from atomic planes according to Bragg's law. N lambda equals 2d sine theta, where lambda is the X-ray wavelength, d is the interplanar spacing, and theta is the diffraction angle. Each crystalline phase has a unique set of d-spacings, creating a characteristic peak pattern that serves as a fingerprint. For nanomaterials, XRD peaks broaden as crystallite size decreases. The Schrödinger equation relates peak width to crystallite size. Tau equals k lambda divided by beta cosine theta, where tau is crystallite size, k is a shape factor around 0.9, and beta is the full width at half maximum in radians. Broader peaks mean smaller crystallites. This provides a quick estimate of crystallite size, though it has limitations. It only works below about 100 nanometers. Strain also broadens peaks, and must be separated from size broadening using methods like Williamson-Hall analysis. X-ray photoelectron spectroscopy provides surface composition and chemical state information. X-rays irradiate the sample, ejecting core-level electrons. By measuring the kinetic energy of these photoelectrons, we calculate their binding energy using the equation E binding equals h nu minus E kinetic minus phi, where phi is the spectrometer work function. Each element has characteristic binding energies for its core levels, enabling identification and quantification of surface elements. XBS is surface sensitive because photoelectrons have limited escape depth. Only electrons from the top 1 to 10 nanometers reach the detector without losing energy. The key advantage of XBS is chemical state information. Binding energy shifts when the chemical environment changes. Oxidized elements have higher binding energies than reduced forms because removing an electron is harder when the atom already has partial positive charge. For titanium, T4 plus in TO2 appears at 458.8 eV, while T3 plus from oxygen vacancies appears about 1.5 eV lower. This sensitivity to oxidation state makes XBS invaluable for understanding surface chemistry. Quantitative XBS analysis requires careful peak fitting. High-resolution spectra of individual elements often show multiple overlapping components from different chemical states. The T2P region, for example, shows spin-orbit split peaks, 2p32 and 2p12, separated by about 5.7 eV with an intensity ratio of 2:1. Each of these can have multiple chemical states. Peak fitting involves several steps. First, subtract the background, typically using Shirley or linear methods. Then identify expected chemical states from literature binding energies. Fit peaks using appropriate line shapes, usually Voigt functions combining Gaussian and Lorentzian contributions. Constrain physically meaningful parameters. Spin-orbit splitting and area ratios should match theory. iterate the fit to minimize residuals. The peak areas, corrected by sensitivity factors, give quantitative composition. Full width at half maximum provides information about chemical disorder. Be cautious of overfitting with too many components. The goal is the simplest model that adequately describes the data. BET analysis measures specific surface area from gas adsorption, typically nitrogen at 77 Kelvin. As relative pressure increases, gas molecules adsorb on the surface in layers. The BET equation describes multi-layer adsorption. P over V times P naught minus P equals 1 over VMC plus C minus 1 over VMC times P over P naught. Plotting the left side versus relative pressure gives a straight line in the range 0.05 to 0.35, from which you extract Vm, the monolayer capacity, and C, a constant related to adsorption energy. Surface area equals Vm times Avogadro's number times the molecular cross-section, 0.162 square nanometers for nitrogen. Results are reported as specific surface area in square meters per gram. Mesoporous silica can exceed 800 square meters per gram. TO2 nanoparticles are typically 50 square meters per gram. Activated carbon reaches 1200 square meters per gram or more. BET is essential for catalysts and adsorbents where surface area directly determines performance. It also provides pore size distribution through analysis of the full isotherm. Comprehensive nanomaterial characterization requires combining multiple techniques because no single method provides complete information. For size and morphology, use TEM for direct imaging and accurate size distributions, DLS for rapid screening and detecting aggregation in suspension, and AFM for height measurements on substrates. For crystal structure, XRD identifies phases and estimates crystallite size through peak broadening, while HRTEM and SAED provide local structural information. For surface chemistry, XBS gives elemental composition and oxidation states, while FTIR identifies functional groups and organic coatings. For surface area, BET measures specific surface area and porosity. A practical workflow might start with DLS to check if colloidal particles are the expected size, followed by TEM for detailed morphology, XRD for crystal structure confirmation, and XBS for surface composition. The key insight is that different techniques can give different answers for the same property, like particle size. DLS gives hydrodynamic diameter, including solvation, TEM gives core diameter, and XRD gives crystallite size, which may differ from particle size. Understanding these differences is essential for accurate characterization. Let's summarize the key characterization techniques we've covered. TEM provides the highest resolution at about 0.1 nanometers, directly imaging particle size, morphology, and crystal structure, but requires thin samples. SEM images surface morphology at 1 nanometer resolution on bulk samples, with EDS for elemental mapping. AFM gives 3D surface topography and mechanical properties without vacuum, working on various substrates. DLS rapidly measures hydrodynamic size in solution, providing PDI for quality control, though larger particles are overweighted. XRD identifies crystal phases and estimates crystallite size through the Schrödinger equation. XBS reveals surface composition from the top 1 to 10 nanometers, with chemical state information from binding energy shifts. BET measures specific surface area from gas adsorption, essential for catalysts and porous materials. In Chapter 4, we'll see how nanoscale dimensions lead to unique size-dependent properties, optical effects like surface plasmon resonance, magnetic superparamagnetism, and enhanced catalytic activity. The characterization techniques you've learned here will help you measure and understand these remarkable properties. See you in the next chapter.